Okay, so hello everyone. So as Pascal said, I'm going to focus on definitional aspects of WHIBOX crypto, and I will describe some security notions that we have proposed to formalize what we could expect from WHIBOX cryptography. Okay, so since it's Sunday and here we're all working, I wanted to start with a little game. So this is an obfuscated program in JavaScript. So does anyone can guess what it does? There is free lunch for.
Hello world.
Hello world. That's hello world. Okay. That's an easy one. Second one. Any idea? Ah, yeah, it's a number. But you knew it. Any idea? So actually, this program, so it's a C program, computes pi. So more precisely, it computes an approximation of pi. And the approximation would be more accurate if this ball was real. So that's just the funny examples I found on the internet. Okay, so now get back to work. So, okay, so this first part is about the definition of cryptographic obfuscation, but it has been covered in previous talk, so I will basically skip it. Maybe just recalling the important things of the virtual black box security notion, which basically consider that an obfuscated program reveals nothing more than the input-output behavior of the program. So here we have this game where an adversary, any adversary that computes one bit of information on the program could be simulated by an efficient simulator that would have only black box access to the same program. Okay? So, as it was said, this kind of program, this notion does not exist in general programs, so you can build like some self-eating programs that cannot be obfuscated under this notion. And the other notion that has been proposed is the indistinguishability obfuscation notion. And as Amit said, it's a bit not very natural notion. At least when you, when I read it the first time, I was a bit puzzled. And I thought, I don't get what it really means. Why would I, compare the obfuscation of my program with an obfuscation of another program? That's not what I want, basically, from obfuscation. And so yes, it was also quickly mentioned that actually I/O is kind of what we could achieve the best. And there is a nice other formulation of this notion, which is best possible obfuscation. So this was shown in a following work. And so this formulation is that anything that can be learned efficiently from the obfuscated program could be learned from any program P prime that is functionally equivalent to the program and that is about the same size. And so formally speaking, that any adversary on an obfuscated program that computes a bit of information could be simulated by a simulator that gets any program P prime input and where P prime is equivalent to a program about the same size. And what is important here is the any, because it means that this program P prime could be the best obfuscated program. So this ensures that the output of the I/O obfuscator is at least obfuscated as the best possible obfuscated program. Okay, so here I just it can be shown that these two notions are equivalent. It is very tight equivalence. I won't go into the details, but basically you just have a factor of 2 in this reduction, so it's great efficient. So we can think of I/O as the best possible way to obfuscate a program. Okay, so now I'm gonna switch to WHIBOX crypto. So I did go into to read the original paper that introduced WHIBOX crypto. So it is due to show it out. It was at GRM 2002, and it was proposing WHIBOX crypto implementation of the DES cipher, where WHIBOX is okay. So the proposal was very close to obfuscation. And so in this paper, it is mentioned that in the WHIBOX model, the attacker is assumed to have full access to the encrypted software and control of the execution environment. So this basically means that we are in the context of obfuscation, definitely. But it is restricted to encryption, or it would be restricted to another kind of cryptographically. It also says our main goal is to make key extraction difficult, and that means that it could be seen, we can see WHIBOX crypto as a relaxation of obfuscation with relaxed security requirements. Meaning that it's important that key extraction will be difficult, but maybe we don't need to satisfy like very strong security notion of WBC, for instance, or IO. And it also says why an attacker can clearly make use of the software itself, forcing an attacker to use the install instance at hand is offensive by you to TRN systems provider. So there is this idea that the encryption software is not equivalent to know the encryption software and to know the key, being having to use the encryption software to constrain the adversary. Okay, so we'll start from this. So we'll think of obfuscation as WHIBOX crypto as obfuscation restricted to cryptographic primitives. And in particular, we could think of SPN ciphers. So in an SPN cipher, we have a linear layer, a key addition layer, a box layer, and this is iterated several times. So this is a very specific kind of program with a strong structure. And we could think that with this structure, we might be able to construct some solution that wouldn't be possible for general programs. And so in the following, our running example will be the class of AES function. And so basically, what does a WHIBOX obfuscator is to take a script key and to construct an implementation of the AES under this key, the WHIBOX implementation. And now, if we try to define what we expect from this implementation, so the strongest possible security property would be the WBC obfuscation, but restricted to AES. So here we would like that any adversary against the WHIBOX implementation basically can do no more than with black box access to the AES under this key. And here the good thing is that the impossibility result that if about does not apply because they are restricted to the class of AES function. And actually we can think of a program that achieves this WBC property. This is the lookup table program, which is just a big lookup table where all the outputs of the AES under this key have been pre-computed and stored. So it can be easily seen that this satisfies WBC, but of course, this is a huge program which actually wouldn't fit the billion terabytes, so it's not practical at all. And so the question is how to build a compact WBC implementation. So it seems to be a very hard problem, and it might be impossible. We don't know. Okay, so now what would IO IOIS mean if we think of IO restricted to AES? So by definition, the IO notion says that if you would have two programs, PK and PK primes, that implements an AES under a key, the IO notion ensures that the obfuscation of the two programs are indistinguishable. So actually, I can give an example of a simple obfuscator that compute that is actually I/O on the AES. So it works as follows. In the first step, we first extract the key from the program PK, and then we return simple reference implementation of AES in this key. So, and this is actually I/O because for two programs that compute AES in the same key, we will have exactly the same output. So, in this solution. Okay, but indeed there is a kind of trick here. It's that this obfuscator might be very inefficient, of course, because of this first step, and we don't know on any program that will compute AES in this key, we would extract the key. Of course, we could use exhaustive search, so we know that this step could be at least computed in 2 to the 128 operations. This would be very inefficient, but it's kind of funny to think that if you consider a case where your obfuscator has unlimited computing power, then achieving this I/O notion can be achieved by this obfuscator, which actually outputs a very insecure obfuscation of the AES. On the other hand, and I think you mentioned that.
Yeah, this is general. Right?
Yeah.
In exponential time, you can always find the lexicographic
Yeah, that's right.
circuit.
That's right. That's what you said. Yeah, exactly. And on the other hand, if some WBC implementation of AES does exist, and if we have an efficient I/O obfuscator, then just applying it to a program by the I/O notion, we know that the program will be indistinguishable from the AES implementation. So this means that the obfuscator achieves as well. So what does AES really mean? Well, I don't know. Okay, so just to sum up, we have this obfuscation scale, where we have here the simple AES implementation, here the WBC AES implementation, we don't know if it exists, and the I/O AES, we don't know where to place it. So in this situation, what we need is something which is kind of relaxed compared to the WBC notion, and which is more meaningful than the I/O notion. So we suggest to propose further security notions for WHIBOX crypto. And so that's what I'm going to talk about now. And I'm going to present some work that we've done towards this issue a few years ago with some colleagues. And what we've done is we take like some folklore idea of what we could expect of WHIBOX crypto, and then from that folklore idea we define some formal security notions. So first I will speak about that. There's folklore ideas trying to answer this question. So what could we expect from WHIBOX cryptography? Okay, so as mentioned, the very least requirement is that key extraction should be difficult. So, however, my point here is that this requirement on its own is really insufficient. And I can show that with a very stupid example where I would consider a cipher that compute AES under a hash value of its secret key. Then I could simply publish an AES implementation with the hash value secret key and say, okay, this is my WHIBOX implementation, and actually it is resistant against key extraction, because if you want to extract the key, you have to invert the hash function. So assuming that the hash function is one wide, you can do it, so okay, that's secure against key extraction. But of course, this is useless and doesn't bring anything in terms of security. So definitely we should expect more than just be secure against key extraction. Okay, I'm trying to define what we could expect. We must have something in mind, is that code lifting will always be possible. So what is code lifting? It just consists in an application taking the code, the part of the code that performs the white box cryptographic operation, and then you can copy it, you can execute it, you can diffuse it. There is no need to prevent that using white box cryptography. But what we could do at least is to make it unavoidable, in the sense that the attacker should be forced to use the software. And if we do that, we can then constrain the software and what the adversary can do with the software. And this can be done, for instance, by putting a software which is less convenient to distribute, which would have restricted functionalities compared to the knowledge of the key, and which also could include some security features. So, okay, so for instance, we could consider that the white box implementation is actually huge and that it should be incompressible. So in that case, it would be less convenient to distribute this implementation. So for instance, we have 10 gigabytes AES, and a possible use case would be ERM. So I assume that some user have some white box implementation that it uses to decrypt some content on like a big device. So we could have a big implementation on this device to decrypt the content, and it would be, of course, less convenient to distribute it, to make it public on the internet because it's big. And for such implementation, we will require that an adversary, of course, cannot extract the key, but also cannot compress the implementation in order to get something smaller, but it can diffuse more easily. Okay, and another way to restrict the software functionality is quite natural, is to make the implementation one way. So for such mission, we will require that the adversary that has white box implementation that encrypt cannot use it to decrypt. And so basically what this does, it turns an AES, the AES, into a public key crypto system. And this could be really useful because it would allow us to get public key cryptography with very lightweight private operations. Just an AES encryption would be very lightweight. We could also apply that to maybe more lightweight cipher. So and that way we could obtain like lightweight signature scheme that would basically perform an encryption to sign, and then publish the encryption white box implementation for the verification. Okay, now some security features that we could include to white box implementation. So a natural example is to add a password to the implementation, so that only the right user knowing the right password can execute the implementation. So what we would require here that an adversary against this implementation that tries to use it to perform an encryption would have to guess the password. So to try all the possible password value. And this would enable to turn a white box implementation in some kind of software secure element. And a possible use case would be payment with token, for instance, where you have some payment tokens that are encrypted, and when you want to perform payment, you decrypt them with the implementation. So the password is asked, and only if you know the password, you can decrypt the token and the payment. So that's just an example. Okay, another security feature we can think of is to include a tracing mechanism. So here the basic use case is pay TV. And so we assume that we have some content which is encrypted and broadcasted. And several users have WHIBOX implementation under the same key to decrypt this content. But we want that if one malicious user, we will call him a traitor, publish his implementation, then we want to be able to trace it. So for this reason, we're going to include something in the WHIBOX implementation, some kind of watermarking with the ID of the user. And here, what we would require is that an adversary from this implementation cannot produce a pirate program. And if it produces a pirate program, we want to be able to know an efficient algorithm to trace the identity of the user that was used to produce this pirate program. And we would like also this to hold if the attacker uses several traitors. So the tracer should be able to recover at least one identity of the traitor. Okay. So now I'm gonna present the way to actually formalize this into security notions. So we consider an encryption scheme as a tuple of key space, message space, encryption, and derivative function. So this is just focus on deterministic encryption. You could think of the encryption scheme as block-ciphers. Of course, we require that the encryption and decryption function are inverse one another for a given key. And so we define this concept of WHIBOX compiler that takes a key and some random tapes, and that produce an implementation of the program computing the encryption function. And we're going to consider an attacker that targets such a WHIBOX encryption program, that output of the compiler for given key and number tape. And we consider several models, so CPA, chosen plain text model, which is basically unavailable because from the WHIBOX implementation, the adversary can write plain text. The CTA model, chosen ciphertext attack, in which the attacker is provided with additional oracle to decrypt ciphertext query. And the recompilation attack model, in which the attacker has also an oracle that allowing to recompile the WHIBOX implementation under the same key and with randomly taken text. And we're going to consider 4 possible goals for this attacker. So the first one is, of course, to break the implementation and to extract the script key. The next goal will be to compress a possibly huge implementation into a small implementation. The third goal will be to compute the inverse of the encryption, so complete the encryption based on the WHIBOX encryption program. And the last one will be to try to be untraced for such an implementation where we would have less than tracing. Okay, so this is the formal definition of the unbreakability security notion. So it's formalized with security game here. We have a challenger that take a random secret key from the tape and compute the corresponding WHIBOX implementation by calling the compiler. Then the WHIBOX implementation is sent to the adversary, and the adversary has to guess the secret key corresponding to this implementation. The attacker is said to win the game if he correctly guesses the secret key. Here I might have access to the oracle depending on the attack model. And so the notion is that we have tau epsilon security with respect to unbreakability if no attacker exists that is able to guess the key with probability greater than epsilon. Okay, so that's pretty basic. Here is a one-wayness notion, so a little bit similar, but the attacker is not given only the WHIBOX implementation, but also ciphertext corresponding to random plaintext, and he have to guess the plaintext. Okay, so notion is defined similarly. Of course, if here the attacker has access, in the case of the CCA attack model, has access to a decrypting oracle, of course, you cannot query the challenge subprefix. So I think it should work. Okay, so now for the incompressibility security notion. So we'll use this notion of distance between a program and a function, which is basically the number of inputs for which the program does not compute the right output divided by the size of the space of input. So this is basically the on random input, the probability that the program failed in computing the function, and this distance is equal to 0 if the program is functioning equivalent to the function. Okay, so here for the incompressibility security notion, so we consider an adversary that gets the WHIBOX implementation that compute a program from this implementation. So what we try to do is to compress this implementation, and we say that we win the game if with parameter lambda delta, if it outputs a program with a distance from the target function, which is the encryption of the key, which is smaller than delta, and if the output implementation is indeed of size lower than lambda. Okay? And of course, this notion only makes sense if delta is pretty close to 0. Otherwise, this means that the output program has a high probability not to answering the right encryption. And if the lambda parameter here is bigger than just the reference implementation, otherwise it would become impossible to compress a program like to get a program smaller than what would be basically required to compute this program. And also lambda should be lower than the minimal size of the WHIBOX implementations. Otherwise, it would always be satisfied. Okay, so now I'm just going to quickly present a toy example of an encryption scheme for which a WHIBOX compiler exists, which is one-way and incompressible. So the encryption scheme we focus on is basically the RSA encryption scheme. So we have the encryption function. So the key is some RSA group for which there is a secret order and an exponent that is randomly drawn, which is co-prime to the secret order. And the encryption is to compute and to the message to be each to the exponent in the group G, and the decryption is to compute the message to the -1 in the order in the group. So this is basically the RSA, but in this formulation, we make it like a secret key encryption scheme. And of course, there exists a WHIBOX compiler, one-way WHIBOX compiler for this, because RSA is the system, everybody know that. But we are gonna, so here our compiler consists in computing a blinded exponent. So it computes E plus some random times the unknown group order. And it simply outputs an implementation that computes M to the blinded exponent in the group. Okay. And so we can show that this compiler is one way in the CPA model. So this is under the RSA assumption in the group. And we can also show that this compiler is actually compressible. And the output implementation cannot be compressed under this parameter lambda, which is the bit size of the blinded exponent. So the idea is that it's difficult to compress the blinded exponent to have another exponent that computes the same, which is equivalent. And we can show that it would mean to reduce this problem, that and we assume that it's hard to compute the order of a random element in the group. This is a very classic assumption of RSA groups. And our security proof also needs that the adversary will produce an algebraic program. That's a detail. So, okay. So I'm not saying here that we came up with a very nice and interesting white box compiler. It was just an example to show that this notion of whiteness and incompressibility are achievable. But what we did actually is that we designed some scheme for which we know some white box compiler that achieve the notion. And to my opinion, if you design a scheme for which an efficient white box compiler exists for whiteness, what you actually do is just designing a public encryption scheme. So it's not, I mean, for me, it's not really doing white box. And you can also, if you design a scheme.
Isn't RSA an existing scheme? I mean, this is an existing scheme, RSA.
Yeah, sure.
So you did design a compiler for an existing scheme.
Yeah, exactly.
Right? Okay.
Yeah.
I thought you were saying your toy example didn't satisfy.
No, of course it's satisfied. No, my point is, if you design the scheme and you say, okay, for this scheme I know a white box compiler which is one way, what you actually did is designing a public key encryption scheme. It's the same with incompressibility. Actually, if you design a scheme for which you know a compiler that's rich in incompressibility, then what you did is design some encryption scheme with some notion which is incompressibility. But my point here is that WHIBOX crypto is about designing a compiler for an existing scheme which does not have the property in the first place. So the real challenge here would be basically to design one way of incompressible implementation for the AES. This would be a real challenge. Okay, so now I'm switching to the traceability notion. So here the typical use case is the page ID. So we will consider a white box implementation of the decryption function. It's the same. We just switch encryption. So we consider. So here the use case is that several users are gonna have some decryption, white box decryption program under the same key to decrypt some broadcast content which is encrypted with the same key. So you need the same key in all the white box implementations. And we're gonna perturbate these implementations in order to be able to trace them. So typically the white box compiler are going to take an additional input here, which is a set of ciphertext. And for this ciphertext value, the white box decryption won't return the actual decryption, but only some dummy value. So for instance, it will just return 0. Okay? And it will work with decrypting all the other ciphertexts. So basically, this set of ciphertext is going to be randomly drawn. So if it's not too big, and it won't be too big, then when using the white box implementation, you will have a negligible probability to actually need to decipher ciphertext in the set. And here is the notion that we will need to be satisfied in order to be able to construct some tracing algorithm. So this notion is called perturbation value ID, PVH, security notion. And so it consists in, so it is for some predefined set of ciphertext. And so it computes a white box implementation with this set of perturbated value in input, and it provides this implementation to the adversary together with a ciphertext that is randomly picked from the set of perturbated ciphertext. And here what the adversary has to do is to guess the real decryption of this perturbated ciphertext value. So it cannot just ask the decryption to the white box implementation, since the white box implementation is perturbated for this ciphertext value, and it won't answer the right decryption. So this is the security game, and the adversary also has a recombining oracle. So it can has new WHIBOX implementations under this key, and with some set of perturbative values that must include the original set. And actually, we can show that if no such adversary exists, then we can compute, then we have an efficient tracing algorithm that would trace any pirate program. So here, so I'm just going to give the general idea of the construction. So we assume that we have n users, and each users have some version of the WHIBOX implementation of the decryption with a different set CI of perturbative values, but they are included either C1 is included in C2, which is included in C3, which is until Cn. Okay? And we consider an adversary that compute a pirate program from T traitor. So we choose T different WHIBOX implementations to compute construct this pirate program. And this pirate program has the distance to the actual decryption function must be negligible. So if you ask this pirate program to decrypt some ciphertext with overwhelming probability, will give the right answer. And we can show that PBH security, so the security of the machine just like before, imply that it is possible to we have a simple linear tracing procedure. So this procedure works as follows. So we consider this probability, which is the probability if you take some ciphertext which is in CI but not in CI -1, that the pirate program gives the right decryption of this ciphertext. And if we look at the curve of this probability, depending on I, the index of the user, then we can show that it starts at 0 here, it reaches 1 here, and it will have some gap only for indexes corresponding to traitors. This can be shown because, so if we take a ciphertext below the index of the first traitor, then in all the WHIBOX implementations, this will be perturbated ciphertext value, and so thanks to the PBH security notion, it is impossible that the pirate program complete the right decryption. On the other hand, if we take a ciphertext which is in a set index which is greater than all the index of the pirate of the traitors, then the ciphertext is going to be decrypted. I mean, all the programs here that will give the right answer to the decryption, so there is no way the pirate going to see that this was a perturbative value. So since the pirate program must be mostly functional here, we have close to 1 probability that we give the right answer. Okay? And the last ingredient is that we can show that between two index of traitors, it is impossible to distinguish if you're here or here. I mean, it will be the same distribution for the input of the pirate program. So this means that here the probability we will have a flat probability. Okay. So basically, we have shown that the only gap that can occur at the index of the traitor, and then we can simply recover such an index with a simple decryption. Okay, so just to finish, I'd like to mention some security hierarchy. So if we assume that we have a secure, cryptographically secure encryption scheme, so it is not hard to see that the one-wayness, incompressibility, and the security security notion implies unbreakability. So because if you can break computation, you can throw the key on none of those notions is key. Also, it is not hard to see that VBD will actually imply the one-wideness notion, the PDH notion. However, it wouldn't imply the incompressibility. So it's, this notion, okay, we thought of VBD as the strongest possible notion, but actually you can find other notions that are not implied by VBD. Okay, so now to conclude, we have so we have seen that WHIBOX crypto can be seen as a restriction of cryptographic obfuscation, so a restriction to a subset of programs. Typically, we consider basically a key permutation, and with relaxed security notion. So I think that more work is needed to refine these notions or to define alternative security notions, and also, of course, to build a candidate WHIBOX compiler that could include these notions. And clearly here, the open challenge would be to design an impossible or one-way or PDH encrypted implementation of the AES. Okay, so yeah, here is the video. So basically, these are the first works of introducing WHIBOX crypto. The works on the notion of obfuscation, so this famous work from 2001, and the work on best possible obfuscation, really worth reading as well. This is 7. The security notion that presented is from that paper that we wrote with some colleagues at SAC 13. And I wanted to mention that some other work previously proposed some security notions for WHIBOX crypto, particularly the what they call the strong WHIBOX security notion, which is the equivalent of the one-wideness that we introduced. And there is also some works on proposing some incompressible implementation. And I think very think about that. Okay, so that's all. Thank you for your attention.